The last part is sequence-to-sequence models. So I'm not going to dwell too much on this, but I'm just going to mention a couple things about this. It's a really useful thing for natural language because, as you probably know, speaking English, is that words change context depending on like the order they have, right? And I think I mentioned about this saying things like, you know, the mouse went across the desk means something different. If you say the mouse went across the desk to get cheese, that cheese part gives you context of the mouse of saying, oh, it's not a computer mouse, it's, you know, an animal mouse. So this is where sequence-to-sequence models are really useful in natural language processing. But it's also really useful, like they're actually developed technically to say it allows you to have different varying input size and output sizes. So this, think of like sentences. Sentences don't all have the same size, right? So you can basically build something that can have a varying size. But this can actually be really useful for applications beyond just like trying to give, well, I'll just tell you some applications and that will make it more sense. So a few things that can do is like we can build sequences for like, as you kind of move up through like time, quote unquote time, like through a sentence, right? You would have new words and that would give more context to the next word. So you can do things like, for example, I don't actually have text generation. So text generation is a really interesting one. So you say like, you know, it was sunny outside, and so I opened the door and then like have like predict what the next word is supposed to be. Like it's based on everything it was previously to the next word kind of deal. We can also do things like stock market, because like in time series and stuff like this, because like basically the things that were previously matter into what is going to happen next, right? If you saw the markets going up in a certain direction, right, your prediction might be different if the market was going down over a certain time and stuff like this. Language translation is also really useful because essentially what you can do, like unfortunately, language translation isn't as simple as just replacing the word with like whatever the word is in the other language, right? It depends on kind of like what was previously said. So you can use sequence-to-sequence models to not just say, okay, this is the current word, translate this. You can say, these were the words that were previously used, plus the current word. How should I translate this? And you can actually build up a language model. So essentially saying, the dog went to the beach or something like that. You can then translate this into French or Spanish or something like that, basically translating, saying, oh, here's the full sentence, translate this each part. So it's kind of an interesting like application of it. There's other things like speech recognition, because basically, again, just language, essentially knowing what the previous sounds were, the previous phonemes technically, will help you predict what the next phonemes are supposed to be. So that can help you be translating that speech, that audio into text. And then an interesting one I kind of put in here that I think most people don't really think of is captioning an image. So there's actually some great papers on this for how you could caption an image. So the idea here is that you feed in like as a seed, it's like your image, and then saying, okay, like, I'm not feeding the image. You feed in the image into like a CNN, and then the CNN will give you saying, oh, this is a different classification. And then feeding that vector of what the classifications are into our current neural network, you can actually build up like a sentence from that input. So you can kind of think of sequence-to-sequence models to take in a couple things. One is kind of like what the event is, and then also feeding in the previous parts. But what's kind of cool is that those previous parts can also be just the prediction. So if I were to kind of draw this out, or, you know, I'll draw it out and then I'll show you a good animation, is that if I have something like this is like kind of like the input right here, and then it's going to say, oh, this is the prediction. So this is the predictions. And I have this event. And it's kind of like, it can feed this information out to the next part. So this is also the prediction. And it can feed into the next part. It's like, oh, well, I know what the previous one was, and I know this current event, this next event, and then it makes a new prediction. So you can think of like, this event could be like a word. It can be kind of like the previous stock market value, or like what the current stock value is supposed to be. And then saying, well, I know this information from prior, and you can take that information and pull it in. So I think it's clear. I think that video I kind of sent out, I think Raphael kind of shared it, and then I shared it with you guys in the cohort. This is kind of like a really quick GIF of it. Basically, the idea here is that they're kind of built up this like scenario where you have either pie or burgers or chicken or something like that. And it's dependent, like usually you would say, oh, I have pie, and then the next day I would have burgers, and the next day I would have chicken, right? And you go in that order, unless it's like sunny. If it's sunny, you just keep it the same. So the idea here is you can build up this neural network that would feed in these parts, and feeding in those parts in there will kind of make a prediction of what the next thing is. And so the idea here is that you would then feed this information. It's like, oh, okay, I had burgers this day. I'm going to feed that into the next part and feed in like the weather. And the weather would be like the event that would be happening. It's like, oh, this is a new thing that's specific to this day, but it also depends on what the previous day is to make that prediction. So this is the idea of having like a recurrent neural network where essentially your prediction will be fed into the next part along with the event. And this would be the event down here. Okay, so this is kind of a nice visualization of like this specific problem. And really it's just a neural network. It's just that it flows back on itself. So this is what we call like a folded versus unfolded. So this folded, this is what we call folded. And basically this is kind of like a procedure of what I'm showing. Like these are the different beds like x0, x1, x2, x2, t. And these are prediction h0, h1, h2, ht, right? All the way through. And this A right here is basically just like, oh, is this like this neural network? This A is represented like all of this stuff right here. And so what's kind of cool is that you first of all take your event, right, which would be like weather, and then make its prediction of like, oh, it's gonna be like a burger, right? And then you would feed this information that you predicted off to the next step. So the next day, for example, like, oh, well, yesterday I had a pie. So, and oh, it's also raining today. So makes its prediction, it should be a burger. Okay. And then it's like, okay, from this point right here, it's a burger. Let's say the next day is like sunny. It says, oh, it's burger was yesterday. Today it's sunny. The prediction should be, you know, a burger or something like that, or whatever the next prediction is. And so you basically are feeding in kind of like the previous prediction as well as the actual event over here. And note that this event can be like multiple features, right? It doesn't have to be like a single, you know, event. And you can get something, we call these like hidden states. So this hidden state basically is the thing you feed into the next part, saying, oh, I learned this information. So this is what we call like a folded model. So just know that whenever you see something like this, basically it represents kind of like this long, long picture. Okay, does that make sense? Kind of seeing what the difference between here and here. I see head nods. Okay, cool. What's nice is that if you think of it in this abstract form, you can first of all say, well, this middle part can be whatever I want. It can be a recurrent neural network, just a neural network, or we can build up specifically how it's going to make those decisions inside. And this hidden state can actually be, you know, multiple information. We can keep feeding that in through it out. What's also really cool, you can actually build recurrent neural networks on top of each other. So you can say like, well, this next part is going to make this next prediction and this next prediction. So you actually can sometimes see these folded models to have like this output here can be its next input into a deeper layer. So you can have like deep recurrent neural networks, which is kind of mind-blowing, but a little too much at once. So some issues with this though, by feeding in the next information, is that it doesn't, how do I say this? The machine learning model tends to forget things. It basically will remember the most recent thing, but if something happens for like over this point, it might forget what happened way back here. And this is where this little animation, actually from this great article, you should read this through. But I think it best explains here is that you can think of this what time is it is the full sentence. And you can see it's represented by this color. And basically the most recent word is going to have a huge, like much more influence than something that's really far away. And you can see kind of like this color here. Like if you look at that last one, it's like mostly red, then a little bit of orange, and a little bit of yellow, then little tiny green, and a little bit of blue. It basically tends to forget these older things. And so recurrent neural networks just aren't good at remembering older things, because it's remembering not just like the previous one, but the previous one, and the previous one, and so on. So there's some ways we can kind of fix this, and the classic ones are long short-term memory cells, or LSTM cells, and gated recurrent units, GRUs or GRUs. I usually hear it as GRUs, but this basically says, instead of saying, oh, we're just going to pass the hidden state, like whatever the next thing is, and usually this hidden state could just be literally be the prediction, you specify in this this LSTM and these GRUs, you specify what you're going to remember. So don't get too intimidated by this, like exactly what's going on here. It's not super important by itself. And then people have asked me like, why is it structured this way? It basically is like, it just tends to work. And that's kind of like the idea. There's some reason behind it, but you can read the paper if you really want to get into it. But the idea here is we still have a hidden state. We have the input. And then this hidden state right here is actually broken into two parts, the long-term memory and short-term memory. So the idea is here, we actually split up this memory that we've been passing recurrent neural networks into two parts. And basically we do certain operations in interacting it with the input to kind of keep like this long-term memory and then what recently happened as well. And this actually turns out to do pretty well in remembering parts beyond like what a recurrent neural network does. And again, there's another article written by the same person who wrote this one right here. But the main thing I kind of want to show is like the input parts are basically the input, right? Input event, the short-term memory and the long-term memory. And then the output is going to output a long-term and short-term. And note that basically we can take these two parts. You can think of it, it's not written in this diagram, but you can think of it as, you can say, oh, this will take these two parts in here as well as the input, right? Let's say this input goes through here. And this will give you like the prediction. In some diagrams, you might have the prediction come out from here. Like you might have another like there's a diagram prediction here. But the idea here is that we have a long-term, short-term, and the prediction at the very end. Okay. So just know that we have these two different parts because they interact differently within the cell. Okay, does that make sense to people? What's going on? Yeah, and the exact details on here, I'm not going to go over. You know, if you want to, you can kind of go through it. I don't think they're super important. They don't really give a huge amount of information, just other than the fact that they're remembering different parts. And know that there's different like gates, for example, like this is like the forget gate. So it takes the non-important stuff and makes it forget it kind of stuff and does the operations on it. And basically the idea here is that we are using, we are specifying the structure instead of having the recurrent network in here, instead of having the neural network to figure out this information. It just turns out it ends up being to be better in doing that prediction. Okay. And then last one, GRUs, which are basically very similar to LSTMs, but basically there's less in it. So we have just working memory. And so we have the input, working memory, and then it interacts with this input, and then it has new working memory. Again, there's nothing, if you look at this doesn't look very different from a recurrent neural network because you have a hidden state. But the main thing is that we're specifying exactly what to do with that working memory. So the sigmoid, this tangent, this pointwise multiplication, pointwise addition, these parts are defined and aren't trained. They aren't changed around as we go over and over again. So this just turns out to be pretty decently. Turns out to work pretty well, even though you don't have as much complexity as the LSTMs. Okay. So yeah, that's kind of like, I would say LSTMs and GRUs are pretty like standard now at this point. I will say though, it's not mentioned in the curriculum. I didn't even put it in here on this part of notebook, but attention models also have been really, really useful. So if you're kind of used to, if you're curious a little bit of like what's the most cutting edge stuff, and cutting edge could be like, at this point, it's like about 1.5 years, but attention models was probably like the big, you know, like the most recent, like big, like, whoa, like this changes a lot of things in the past like 2 years. But that's another way of basically saying, oh, you should pay attention to this. And this, it's a little more complicated, but the idea is that we're keeping the idea of saying, oh, this is an important thing. So remember this stuff as you kind of make more predictions. Okay. Cool. So that's kind of overall what I had. Do you guys have any overall questions about sequence models for recurrent neural networks, LSTMs? Yeah. The main thing is, I would say, if you will see in the curriculum, if you try to implement an LSTM, you're basically just calling another function that's going to do all this for you. If you get really into it, you can actually start playing around with like the different structures stuff like that and see if like maybe you can, you know, define different parts. But for the most part, I would say you probably wouldn't do this unless you're a researcher. So the main important part is just knowing that a sequence model basically takes in an event, takes in some kind of hidden state, basically its memory, and puts those together to make a new prediction, and then passes its information, this hidden state, to the next element, and do the whole process over again. Okay, cool. All right, so I guess I'll go ahead and stop recording here if you guys are cool with that. Yeah. Actually, I don't know how to stop it now. Oh, there we are. stop share.